Welcome back. Today we are talking about the end-to-end flow of a microservice solution. In a nutshell, from code to operations. My partner in crime is Gianni Rosagallina.
Hello, good afternoon everybody.
Our special guest is Fabio Lonegro.
Hello everybody.
And our support for the technical panel for answering your question is Max Giovagnoli.
Hello everyone.
Okay, before starting with this talk, let me remember you that you can interact with us simply by adding a comment below. Okay, Fabio, we can share your screen?
Yes, the usual live effect. Sorry, just 1 second. Let me start giving a couple of details about me. Well, I am Fabio Lonegro. I work in Delta Thread since 10 years, more or less. I'm cloud architect here. Just 1 second. Let me go full screen. Okay, so first of all, thank you for the invitation. It's a pleasure to be here. As I said, a couple of bits about me. As I said, I'm cloud platform architect here. I've been a software developer for some years, working with many stacks, and I am really happy to be able to work with Kubernetes, especially for the opportunities that Kubernetes offers nowadays, not just looking at Kubernetes as a simply as a new way to deliver our applications. This is the brief outline of what I'll be talking about today. So let's get started. The starting point is DevOps. So DevOps has been around for quite a lot of time now, and probably many of you already know what DevOps means. Essentially, it is an approach, something like a philosophical or a cultural approach to the end-to-end workflow for developing and managing applications in real environments. There's really nothing to explain about this diagram. Essentially, what I would like to focus on is the fact that DevOps relies on some simple concepts. It's a combination of development and operations. So we need to make sure that we have a good collaboration between development and operations teams. It's all about continuous iterations of essentially following this loop over and over again. And since it is quite clear the approach that DevOps describes, it's all about automation. So we should automate as much as we can following this approach. Probably many of you will recognize this workflow. It is essentially how traditionally we have been implementing CI/CD workflows in our activities. Essentially, there is a team, the concept of a team, at the very left-hand side of this chart, pushing some code to a code repo and making sure that code is reviewed using pull requests and similar approaches. And usually we have triggers, and triggers are responsible for invoking CI pipelines, continuous integration pipelines, where code is built, tested, analyzed. Tested, please. Let's test our code. And where usually we create our artifacts. Our artifacts are essentially, I will focus on essentially images, Docker images, that are eventually pushed to an image registry, a Docker registry, something like that. Then this is a simplified view, of course, but somewhere else we have something like a config repo where we define what has to be delivered on our actual environments, where our code will run eventually. So just a simple comment: up to the the image registry push, our code essentially doesn't know nothing about where it will be running. It's only in the second part, from the config repo on, that we introduce things like the environment where the code will be running. And again, using more or less the same mechanism, this is why the two flows are very similar, we start continuous deployment pipelines, where essentially we combine our images with additional things like, config maps, services, ingresses, and similar additional concepts. And we essentially publish everything to our Kubernetes cluster. This config repo can be something like a repo where we have Helm charts or similar things to describe our how our workloads will run in the environment. Let me just focus on some challenges that this approach brings in. The first one is release responsibility. Well, there is a similarity between the two flows, CI and CD, but when you work with some very limited environments or some restricted environments, you may need to pay special attention to the delivery part. So when you work for government or banks or something like that, you have to care about, you have to pay special attention. I'm not saying this is impossible. I'm just saying you have to care about that. The process of moving artifacts from one environment to another one, the idea is that, following the 12 factors for software as a service, environments should be similar. So we have to keep them consistent. So there is this concept of moving artifacts from one environment to another one. Again, this is not impossible with the standard approach I described, but again, we have to pay attention to that. One of the challenges that we have to face is when the number of environments increases. So it's quite easy if you have to deliver to a single Kubernetes cluster. Things may be a little bit more complicated when you have a dev environment, a staging one, and production. Maybe production is replicated because you want to have high availability and similar things. But let's say, what happens if you have to deliver your software to, I don't know, IoT devices or kiosks in all the New York cafes, something like that? You have to know all of them. So it brings this concept of scalability of your CD pipelines. What happens if someone or something goes directly to your actual environment and makes some changes? These kind of changes are not controlled by the event that starts the CD pipeline, so you may end up with a system that is not in sync with the initial definition. There is this concept of kubectl being the modern SSH. Okay, this is more or less the same kind of problem we had ages ago. And finally, something that is essentially reminded by the previous point: what is the source of truth for the state of your system? The system itself? Well, you have to query your system to understand the state. Well, this is not ideal. If you want to understand what was the state of the system a week ago, clearly you don't have this capability by just querying the system. The guy that manages the deployment, again, please don't. Documentation, well, I don't want to even spend a word for that, because documentation can lie, while code never lies. So all these challenges somehow suggest that the CI automation is similar in terms of what can be done with this kind of automation, but in principle, it is quite different from CD automation. And this is where GitOps can be considered. And this is more or less the historical concept that has essentially that has been leading to the definition of GitOps. So what is GitOps? In simple words, it's a again, an approach. It is a little bit more specific than DevOps. DevOps is just a set of principles. GitOps also contains something very specific, like a Git repo, where we keep all the versions of our system. In this, we describe it in a. This is key for GitOps. We describe the state of the system. We don't describe how we have to obtain this state. So we have a snapshot of the state, and then there is the concept of something, some code in the end that is responsible for continuously compare the desired state version in the Git repo and the observed state of the system, and eventually react if something changes. The reaction can be a simple, alert, or it can be a real reconciliation. So it is possible with this approach to have to remediate to the fact that the system has changed. So going back to the challenges, how can GitOps help solving or addressing these challenges? Well, first of all, the desired state in a Git repo allows introduction of a very specific model for approving changes. This is the standard pull request mechanism, which is mature, and everyone, at least in the development side of the world, is very aware of. The fact that we can introduce a reconciliation actor, well, the reconciliation actor, being close to the actual state of the system, can actually run in the system that it has to monitor. And so this allows essentially the possibility to invert the flow. And so instead of pushing to the actual environment, we can have this component pulling the desired state from the Git repo. This is essentially key for GitOps. This becomes highly scalable. So if we have to manage many environments, well, this is quite easy. We are scaling the consumers, the environments, instead of parallelizing the CD pipelines. It is more secure because your CD system doesn't have to know somehow the connection strings, the credentials to access the real environments. In this case, the CD system can become a surface attack. The reconciliation in case of untracked changes is built in with this reconciliation loop. And finally, well, release promotion comes for free because every environment is simply looking for its specific state. So we don't have to move things. It's the environment itself that simply pulls the right configuration. Well, this is the standard diagram. This is essentially how GitOps, the GitOps interpretation of the DevOps workflow. So the orange part is essentially the standard CI stuff that we used to know. And the blue part is how GitOps works. Essentially, pulling from the Git repo, we have deployments. It can be more or less everything. It can be the infrastructure. It can also be the applications running in our specific infrastructure. We can monitor and trace everything, and we can operate on by simply managing this Git repo. Again, it doesn't come without challenges, of course. The first one is how we manage secrets. Well, this is probably the first challenge that we have to face. We are saying that the state of the system, everything, should be versioned in our Git repo. Should we also version secrets there? Well, yes and no. There are approaches for that, but for sure, this is something that we have to care about when using the GitOps approach. This is a little bit more hard to see, but I don't want to spend too much words for that. But essentially, it is a problem about concurrency. So when we have many different workflows impacting the same Git repo, there may be some possible conflicts with the state of the system. I'm not referring to conflicts in Git. I'm referring to conflicts in the state definition. Well, somehow, given the central role of Git, we may face the problem of having many Git repositories to manage. Again, these are not issues. These are just challenges. We have to have a real strategy for all of them. Okay, so this is the basic introduction. I would like to go to the definition of this prototype, the prototype that I'd like to present you today. So the main idea is to use GitOps to create a distributed system. Distributed system is essentially, it can be seen more or less as a microservices architecture. So you have many microservices that can interact in some kind of way, synchronously, asynchronously, but essentially we have distributed systems that cooperate to get the final, to meet the final requirements. The idea is to have a front-end web application with a simple UI that allows you to save and retrieve saved items. Very simple. The way this front-end application interacts with the persistence layer is using some REST APIs, server-to-server APIs, that in the end use Redis as backend system. And this is just let's say the application side of the story. Then I would like to use Flux v2 as GitOps controller. Flux v2, a couple of words about it, is essentially the version 2 of Flux, as the name suggests. Flux has been developed by Weaveworks, the ones that essentially introduced the concept of GitOps. Flux v2 is not just a tool; is a they refer to Flux as essentially Flux is built on top of the so-called GitOps toolkit. Many different components that together work to ensure that the GitOps workflow is effectively working in your environment. And I will use a remote AKS cluster. My initial idea was to use Kind, but my laptop will suffer too much for the extreme virtualization, so I will use a remote cluster. What is the actual setup for my Git repositories? So I have to version my code. I have one code repo for both applications, the front-end application and the APIs. I know this is not a very good practice, but I want it to be somehow fast, so I condensed both in the same place. Again, this is not a good practice because there is the risk of coupling too much things and create essentially a distributed monolith, which is the opposite of essentially of a microservices architecture, but I'm aware of that. I'm trying to keep things separated. Every service has its own Helm chart, very basic Helm charts. I've not spent too much time optimizing the Helm charts. I just wanted to have a place where essentially I can fetch my applications together with all the accessories that they need, and a GitOps repository where this is essentially the Git repo that is in the middle between development and operations, and it represents somehow the immutability barrier, the firewall. Okay, so every change should be done strictly using the GitOps approach by simply managing this repo. Okay, I will give you an idea of how these repos are structured, but for now, let's go on with the presentation. So the high-level setup is this one. So this is what I want to obtain. So I have my GitOps repo here in GitHub, in my public GitHub. And here I have this Flux controller. Essentially, this is a set of controllers, but let me refer to them as simply as Flux. And I want Flux to deliver inside the cluster my front-end application that will talk in HTTP to my APIs. And the APIs are, again, delivered using Flux, and also a very simple Redis chart for Redis Helm chart, and the APIs are talking with Redis using the standard protocol using TCP. And I want to have this, so essentially north-south communication from the outside world is done, again, with simple HTTP. Okay, so how can we start and set up our environment? Well, Flux is, as I said, is a set of controllers, essentially operators in the Kubernetes language, that run inside a Kubernetes cluster. But to bootstrap this, well, Flux provides a very useful CLI that essentially, well, its first task is to bootstrap the cluster. It creates somehow the connection with the GitHub, with the Git repo, and delivers, this is funny, using a GitOps approach, Flux itself inside the cluster. So so again, the Flux configuration is stored inside the Git repo. I will show you that in a moment. So Flux can monitor in principle any Git repo, GitHub, GitLab, private Git, or something similar. In my specific case, I'm using GitHub, and I need to provide a GitHub token as an environment variable to the Flux CLI to make sure that the Flux CLI can provide the right permissions to the Flux controllers. And I don't know if you can actually see what I have here. It's a bit small, I know, but well, essentially, I would like to simply mention that this is the command that I have to run to make sure that, in the context of my cluster, I can instantiate the Flux controllers. So I'm simply referring to a GitHub repository, and I'm just specifying a path inside the Git repository in a specific branch where the Flux definition will be stored. So when I run this command, essentially what I get is inside my cluster, when I get the pod running after running this command, what I get is essentially a set of controllers. These are essentially the controllers that together define the so-called GitOps toolkit. Well, there is a source controller. This guy is essentially the one that constantly checks the Git repo and is essentially listening for changes there. There is a notification controller, self-speaking. Helm controller, this one essentially is again an operator that monitors somehow some specific custom resource definitions, Flux specific custom resources that somehow abstract Helm release and Helm repositories. So it is possible using this controller to fetch this abstraction of the Helm release and make it concrete inside the cluster as a Helm release. The same the same is true for this guy, the customized controller, that is essentially doing the same things but for customized instead of Helm. Again, still talking about the definition of this prototype, I wanted to add something more. So in the title, you've seen safe, secure. So I want to introduce some level of security. I don't want to have Redis without authentication. So I wanted to introduce Redis authentication, and also an API key on my REST APIs, even if they are not accessible to the outside world. I wanted to have this specific additional level of security. Well, this means that the front-end API, the front-end component will need to know the API key to talk with the APIs. The API will have to know the Redis authentication to talk with Redis, and they also will have to know the API key because they will have to validate the API key at every request. And clearly, the Redis Helm chart will need to be instructed with the authentication key. This essentially opens an important discussion about secrets. What is clear from this simple table is that, well, first of all, secrets are not for everybody. Okay, the idea of okay, if you tell a secret to my mother, you can make sure that tomorrow everyone in Torino will know about that secret. So you have to keep secrets somehow secrets. So you have to provide your secrets to the components that actually need them. So it's useless and actually risky to provide somehow the Redis authentication to the front-end application. This is useless and can be again a surface attack. Very generic definition of secret. By secret, I mean essentially sensitive data that allow in some kind of way the access or to keep secure the communication between systems. It can be essentially database credentials, API keys, certificate, SSH keys, and similar things. I'm not referring to user data. This is a different thing. Okay, how can we manage secrets? With GitOps, there are at least a couple of approaches that can be adopted. The simplest one is sealed secrets. Sealed secret is again an operator, a Kubernetes operator, that when delivered inside a cluster, essentially creates an RSA, an asymmetric key pair, a private and a public key. And using a companion CLI, you can essentially retrieve the public key from the sealed secret operator. This public key, being public, can be safely stored inside even a Git repo, and it can be used to encrypt standard Kubernetes secrets. So you have a plain Kubernetes secret, the YAML definition of it. You can simply encrypt it using the CLI plus the public key. You can upload somehow or pull the secret using the GitOps approach inside the cluster. Then the controller will essentially use the private key, which is stored safely inside the cluster, and will decrypt the secret and will transform it back to a standard Kubernetes secret. And when you have a Kubernetes secret, you can do pretty much everything you are allowed to do with a Kubernetes secret. You can mount it as a part of the file system of the pods. You can do these kind of things. There is another approach. I'm referring here to a specific tool called Hashicorp Vault. Hashicorp is, well, the company that is behind Terraform, for instance, but not just Terraform. Hashicorp Vault is another interesting tool. Essentially, the Hashicorp Vault is a tool that can store secrets, but can do something more, actually. We have to lose something to get this additional level. It is possible with Hashicorp Vault to define some specific policies. And this is actually what I wanted to have. So I wanted to have a specific policy that prevents, in somehow an easy way, for instance, the front end from having the Redis password. Okay. So again, it can be combined with additional authentication mechanisms. You can authenticate people using external identity management systems like, I don't know, Active Directory, Facebook, whatever. But it can also authenticate services like applications running inside the Kubernetes clusters using clearly a service account. Some of the features, it can provide dynamically secrets injection. So you can inject into your pods a secret dynamically. Secrets can be revoked. This is another funny thing. There is a full and rich audit log for all the secrets requests. So it can be easy to track when a secret has been leaked or similar things. It can be completely decoupled from the applications cluster. So if you want to run the Vault inside the Kubernetes cluster, it doesn't have to be the same cluster where your applications are running. It can be completely decoupled. Actually, this is the good practice for that. It doesn't have any impact on the applications development. So applications don't know where secrets come from. So they only require some specific, environment variable, again, following the 12 factors, or some configuration file. But again, they don't know where these secrets come from. It also provides some cryptographic APIs if you don't want to implement your own cryptographic things. This is high-level workflow of how the Vault can provide dynamic secrets to your running applications. Essentially, when you deliver your application inside Kubernetes, you provide a service account. This service account tries to authenticate itself against the Vault, but the Vault will check the token, essentially the service account token that lives inside the pod, against the Kubernetes APIs. And if the authentication is successful, the Vault will provide back, again, a token. And this token will contain essentially some policies. And these policies can be used to check whether the application has access or not to a specific secret. So this is a way to effectively manage who can access what, essentially. So it's a way to enforce some policies on the access of to specific secrets. And policies can be very complex policies. You can be simply a read-only policy. You can allow writing secrets. It can be very, very complicated. At least you can list secrets. You can do pretty much everything, but you have to specify this in a policy. Again, probably too small, but essentially the way you can engage the secrets injection capability is using simple annotations. The Vault, when delivered inside Kubernetes, provides an additional component that, using again a native Kubernetes mechanism, mutation webhook controller, essentially it can check that a pod is starting. And when pods are starting, if they have some specific annotations, this component of the Vault ecosystem essentially can inject an init container inside the pod. And this init container will perform this authentication workflow against the Vault and will then ask for a specific secret. And again, as you see here, I need to specify a service account. For essentially, a service account defines a group inside the Kubernetes with respect to the Kubernetes authentication mechanism. And then, essentially, when I received my secrets, so when I'm sure that everything has been done properly, so if the init container fails, there's nothing to do, of course. The pod will not start. Will not be ready at all, will not be running, actually. So I need to change somehow the entry point and the command of my Docker image to make sure that I can effectively use the secret that sorry, let me go back here. When I get the secret, I can create some specific file inside the file system of the pod. So it's actually this authconfig JSON. And then I can use it. This authconfig JSON can be used, and this is specific to the application. The application is able to read this specific file format. So the application will start and everything will already be there for to be consumed. And the application will never know where the secrets are coming from. This is, again, the cool part of it. So is one approach better than the other? Well, they can work together. So sealed secrets and Hashicorp Vault can work together. I just decided to use Vault to provide this fine-grained access to my secrets. But, okay, this is very specific. The Hashicorp Vault, when it is initialized, it creates five keys. You can think about a bank where the keys for the Kavo are more than one, and one is given to the director, another one to the responsible of the security, and another one to I don't know. And only when you have at least 2 or 3 of them, you can open the Kavo. This is more or less the same approach. To be ready, the Hashicorp Vault needs at least 3 of these keys. So how can we solve this issue? So since we are living in a Kubernetes world, pod can be killed by the orchestrator. So when a pod gets killed and another one gets created, we don't want to provide again and again 3 of these 5 keys to the pod to be up and running. Well, it is possible at this point to have a very dedicated approach. So Hashicorp Vault can essentially be coupled with a key storage, and in principle with any key storage like Azure Key Vault, AWS Key Management System, and similar things for GCP. So one key, a cryptographic key, can be stored inside the key storage, and this key will be used to encrypt these 5 keys needed by the vault. And when the vault gets killed, for instance, and another pod of the vault starts, this pod can use the communication with the key storage, fetch the key, decrypt the 5 keys, use 3 of them, and start. Well, it's a bit tricky, but essentially it moves the complexity of managing these cryptographic keys to something else. But again, we have a problem. How do we provide access to the Azure Key Vault, in my case, to the Vault? So if Vault is supposed to manage secrets, and we need a secret for the Vault to communicate with the Azure Key Vault, who is responsible for providing this secret? Well, in this case, I used sealed secrets. Okay, and this is how the 2 things can be combined together. Then I did something inside my vault. I created a specific configuration to make sure that I can provide secrets only to the right applications. I will run a little bit for this part. So essentially, the final architecture that I want to have in place is this one. So in terms of GitOps, I will have Flux delivering sealed secrets, the Vault, the applications, and Istio. Istio because it simplifies a bit the network communication inside the cluster, and will also provide a way to expose HTTP traffic to the outside world. Secrets injection works in this way. So sealed secrets will provide the secret for the Vault to communicate with Azure Key Vault outside. And then when the Vault is up and running, it can provide the right secrets to the right applications. And finally, the HTTP flow is something like that. So I will use Istio as service mesh, very basic setup, plus ingress gateway here. So actually, the communication with the front end will go through the ingress gateway, the Istio ingress gateway. Final considerations. Well, of course, we need to make sure that our software is always validated with tests and during all the phases of the development. But in many situations, it is a good practice to have a safe way to roll out our applications in production. This can be canary releases, blue-green, A/B testing, these kind of things. Well, it turns out that Weaveworks, the same company that is behind Flux, is also providing a very cool tool called Flagger. It has been developed by Stefan Prodon. Essentially, Flagger is another kind of reconciliation controller that lives. It's a runtime reconciliation controller. It lives inside the cluster, and again, using webhooks, it can understand when a new version of a specific application has to be delivered to the cluster. So when there is the request to deliver a new version of a specific application, Flagger can intercept this request and create and essentially apply traffic splits for this application. It can make sure that the rollout of the new application, for instance, in a canary scenario, only happens when all the KPIs are successful. So I can decide that, for instance, I want to have an error rate below, I don't know, 5%. I want to have latency below 500 milliseconds, something like that. If these requirements are not met, then Flagger is able to roll back the new delivery. Otherwise, it can progressively, step by step, increasing the traffic that goes to the new version, effectively roll out the new version and remove the old one. This is the very basic diagram of how Flagger works. Additional bits here. I decided to also have Prometheus. Well, as I said, Istio for service mesh and Ingress gateway. I want to have Prometheus for metrics, Grafana for, well, to visualize things, and Kiali, which is another cool tool that can help understand what happens inside the cluster. Demo time. Okay, so I've been running a bit because I wanted to present many concepts together, but maybe now they will all make sense, or maybe not. Okay, if my laptop helps me. Okay, sorry, just 1 second. Okay, so this is the structure of my GitOps repo, and this is the situation right now. Sorry, I'm a bit nerd. I like to have many different consoles at the same time, but essentially, top left corner, you can see the running pods. You may see here in the Flux system namespace, we have the Flux controllers. Then I already delivered, to speed up the demo, sealed secrets. You know, it's older than the Vault because the Vault needs sealed secrets. Then I have the Vault in high availability. And, well, I also deliver Istio, well, the Istio operator first, and then Istio itself with all its add-ons like Kiali, Grafana, and Prometheus specifically. And, well, this is essentially the definition. Let me increase the font size here, otherwise. Come on. Okay. So what happens now? So this is the folder where I bootstrapped Flux for this specific, you can see it from here. Sorry, this is the lab AKS cluster that I'm using right now. And this is where I'm versioning things. I have inside the infrastructure definition, I'm basically referring to something that lives inside the Git repository called Flux system, which is essentially this Git repository. To something that lives in this folder, I basically have sealed secrets. Sealed secrets is defined. Well, these files here are just index files. You can consider them as index files. So there is a Helm repository, a specific Helm repository, the Bitnami one, where the Helm chart for sealed secret is stored. And then I have a specific release for this Helm chart. What does it mean? Essentially, we have a Helm release. This is a description, complete description of essentially what the Helm controller in Flux will translate into something like Helm install. Okay, so essentially these instructions will be translated by that guy into something Helm-like. This is again a custom resource definition in the Flux namespace, so something that Flux can really understand. As you may see here, I have a couple of clusters that I'm managing here. That's what the reason is that I had to test things before. As you can see, I also have the Vault already installed here. The only thing that is missing is the apps, okay, which is not present here. And this is what I want to show you now. Sorry, one second. Okay. So let's try to see what happens if I bring in the apps inside this lab definition. Okay, everything is commented now. I want to save it. This is a shortcut for add everything and comment with a message. This is a shortcut for git push origin master. So I'm doing basic things right now. I'm just pushing to a Git repository. If my laptop wants to follow me. Okay. Come on. Okay, so let's check what is happening here now. We will need to wait because the reconciliation loop for the source controller is a specific interval. I think right now it has been set to 1 minute. So no more than 1 minute to see something happening. Okay, so something is already happening. As you may see, we have these 3 guys. They are all named Platform Lab. So we have the front-end application. You can see that there is an init process, one of 2. The first init container that is starting is the Vault one. So the one that is responsible for asking the Vault authentication and receiving somehow the secret back. And the second init container is simply the Istio sidecar. Sorry, it's not the Istio init container. And then we end up having two containers inside these pods because, as you may see from here, default namespace is labeled with Istio injection enabled. So essentially, Istio will inject its sidecar inside pods living in the default namespace. Okay, so we've got this situation. Everything is up and running, and well, essentially, I don't want to go to the public URL of this application. I can simply port forward the front end application and see what happens. Come on. Sorry, this is usual live effect. Please forgive me. I'm running my application on port 80. It is also running as root inside the container. I know this is not a very good practice, but please, again, forgive me. Okay, I can maybe show you what happens here. If you're lucky, the application should start. Yeah, it starts. And okay, this is the basic interface I was referring to. I can, again, it's a prototype. I can save items here. Again, if I'm lucky, okay. So you see this is persistent because we have Redis behind the scenes. So if I refresh the page, things are stored there. And okay, if I go back here, you may see I'm constantly running a watch command to get the canary resources in the cluster. And actually, I have this platform lab API that is the canary definition for my APIs. This means that I have defined inside the Helm chart of my APIs a specific resource, the canary resource, that is the one that the Flagger controller constantly checks to understand what kind of behavior it has to apply when a new version of the API gets delivered. So one of the things I would like to do now is, okay, I would like to start a very simple load test on my API, simulating somehow the traffic that I have on my application. So let me just start. Let me just start a very simple load test here. You don't have to care about these details, but essentially what I'm trying to do now is something like that. I'm hitting the localhost 8080 with 50 requests per second. This is what I'm doing. Well, you can even not call it a load test. Okay, I'm pretty close to the end. I would like to show you again, of course. I need to port forward Kiali. Sorry for that. I don't have. I didn't have time to expose everything to the outside world with proper authentication. But the way I can port forward Kiali is quite simple. It's something like that. I need to expose the right pod specific port. So we should be able to see Kiali now. Kiali is a very, it's not authenticated. We should be able to see the traffic coming in because let's see, for instance, traffic animation. As you may see, there's something that goes to the front end pod, goes to a specific service here. Triangles are services and squares are pods essentially. And this is how things are working. So the front end is calling the APIs. Everything is green because there's no problems in the application, and it goes to the APIs, and then the APIs are talking TCP with Redis. So what I would like to showcase right now, very, very simple. What happens if now, okay, this within the lab, the apps definition refers again to something that is stored within a Git repository named Flux system, again, this repository. And it refers to the folder apps, which is this one, that consists of, again, Redis front-end and the APIs. And the APIs, the release of the APIs, as you may see, there is a specific section inside this Helm release custom definition that specifies the values for this Helm chart. I created this application with an intrinsic and programmatic way to create errors. So this flackiness is essentially the percentage that of failures that the APIs can. So essentially, if I specify 10 here, it will mean that 10% of the calls to the APIs will fail with a 500 error. Okay. Otherwise, unless Redis is down or something bad happens, this with 0%, the API will always respond with a good result, with a 200 result. So I also defined for the canary stuff, which is this part. So the canary part can monitor essentially two different metrics, the error rate and the latency. The latency is currently disabled because the error business that I injected in my application is based on the error rate. So what I'm saying here is that my canary will be successful if the error rate is below this threshold. So it's below 50%. Okay, so let's try to see what happens if I specify something very bad. And I say that my application will have to fail 75% of the time. Again, what I have to do to manage my application, this is essentially a simulation of a bad version of my application, something that I didn't discover during the development phase or during the test phase, but it's something that I can discover in a real situation. So again, let me add everything, comment, and add the message. 75% flakiness, and then push into master again. Let's check what happens here. Okay, pay attention to this, essentially to this guy here. Again, we will probably have to wait some seconds because the loop is set up to 1 minute. Well, something else that I can do, I can also show you the Grafana while we wait for that. We can also see what happens with Grafana. And I'm just port forwarding things on a different port. If, again, my laptop helps me. Okay, while we wait, okay, so Grafana, it has been delivered with a set of specific dashboards for Flagger and the Canary releases. Currently, as you may see, we have 50 requests per second with a success rate of 100%, because it was the initial delivery I had. You can see now that since 16 seconds, there is a new pod for the lab APIs, okay? And here, the state of this Canary release is now progressing. And it is currently moving 5% of the traffic to the new instance, okay? So this is somehow protected. We are not moving everything to the new version of the application. We are just routing there a part of it. This will be visible probably soon. You can see here that something is happening from here, and we will see, okay, something in the incoming requests here at a certain point, probably. Again, if my okay, oh, sorry, I had to refresh, but it's already there. And Chiali should be able to show that. Okay. Let me hide something that is not really needed for that. But you can see the traffic split here. So we have the first path, which is the green one. And the green one is completely successful. You can also see from here that we have 100% of OK. And here, the Canary part is actually failing with more or less, you see, something close to 75%. It is based on a random number, so don't expect an exact amount of failures. This is also visible here. You see we have 2 requests per second out of 50. So more or less 5% of the traffic is going to the second version, to the Canary version, and we have a success rate which is around 25%. So if we monitor what is happening here, this is still progressing. The analysis is still ongoing. It can be fine-tuned. You can specify the amount of time that you are that you want to wait until the analysis is done. But essentially, if things will go as I expect, we should see a rollback of this application to the initial state where we don't have any errors. Well, while we continue monitoring this, and again, it's probably something that I have to fine tune to give a better effect. But well, essentially, this concludes my presentation. So we can probably check again in a couple of minutes, but we can, well, I can leave here and open to questions. Okay, it failed. Okay, it finally failed here. You can see here, and this new pod, the recent one, the one that has been delivered 3 minutes ago, is now in terminating phase, and it will be killed at a certain point. Okay, so the traffic in Kiali, here in Grafana, we can see that everything is moving back to 50 requests per second, the current traffic that I'm defining on my application. And Kiali, okay, it is refreshing every 15 seconds, but we will see in a moment that this part will be removed, because there's no other option, because it will not be there at all. You see the connection to Redis has been dropped, and at a certain point, this path will be completely removed. Of course, I'm not showing you the positive case when I deliver something that actually is successful enough. It can be done. You will essentially be able to see that this progressing state will increase the weight from. Again, this can be configured. I can define up to where I want to open the traffic progressively, and when I reach a certain threshold, I can say, okay, everything is fine. I can completely roll out my new application and remove the old one, because I'm fine with that. So this is essentially a way to discover things in production and be safe. So you can have something that does the job for you, that rolls back everything if something bad happens that you didn't have the chance to discover before. And well, again, that's it. That's the end of my presentation.
Thank you, Fabio, for your overview. I believe that your presentation is very, very good for people like me and Johnny that worked on prototype, but never managed on secrets, issues, and related problems. Anyway, Max, you are a DevOps.
Yeah.
What do you think about all this stuff?
Yeah, I think that this is all very, very brilliant. I generally I like a lot the GitOps approach, because I think that it puts Git in a focal point where everyone can collaborate, can put documentation, declare new desired state, and this is an enabler of very simple collaboration, and also enable versioning in a standard way now, because this is, at least now, Git the version control system standard. And I didn't know actually Flagger. I liked a lot. I'd like to have a monitor dedicated only to Flagger traffic control. And this is something very, very cool. And yeah.
I also liked a lot Kiali. I didn't know about it, but also showing all the path, the routing path, and where request goes, where they fail, is very interesting to know. As Clemente was saying, we are used to build architecture prototypes, so never move at that level of complexity in production. But knowing that there can be best practice like this one to follow also in prototyping, will enable a lot of projects to move faster from the prototype or POC phase to production when needed. If we start with this all this stuff already in place.
Yeah, as essentially, I think that this, again, Kubernetes is acting as a catalyst, somehow we should somehow, if we are just thinking about Kubernetes as a simple way to deliver things to a different platform, well, it's not. Actually, we have the possibility to leverage the capabilities that Kubernetes offers, because many of these things, well, for instance, the reconciliation loop is something that is built in. It's not new, because Kubernetes is not the first platform that uses the reconciliation loop. But the fact that you have, it's a very simple fact. When you have a deployment, for instance, and you specify that your deployment should have like 4 replicas, and you kill one of the pod for some reason, well, the deployment following the reconciliation loop essentially will create a new pod to match the desired state that you declared within the deployment manifest. So this concept of reconciliation loop is all around this GitOps approach. Well, there's clearly 2 different reconciliation loops. One is for for state reconciliation, and another one is runtime reconciliation, like deployments or like Flagger is doing. But the fact that this is a first-class citizen, in my opinion, helps introducing additional patterns for the management of our applications. There is a very cool talk given by the CTO of Weaveworks, like some months ago, not more than 6 months ago, and essentially there is a clear, very simple description of the possible patterns that can be introduced. Like, you can also monitor the Docker images that are specific for one of your applications using GitOps, and essentially you can immediately bring them in. So you can specify a policy where you can already update your images, your Docker images inside your cluster, but you can also do something more in line with GitOps. You can let the reconciler, when the reconciler understands that there is a new image available, it can, since it knows that there is a Git repo, it can also create an automatic pull request to say, hey guys, there is a new version of this application. Can you think about merging it and make it available there? Well, this can actually be something that can push the reconciliation patterns to a next level, actually.
Let me share your GitHub. Here you can have a look to the code, to the interesting examples. And let me remember that this presentation is the first part of a series. So, Fabio, can you spoiler some things for the next presentation?
Well, I've been lying a bit with you. Well, the reason is that I've been running a lot during this. So someone will probably slow down the playback. I know that, but I try to concentrate everything. So because I wanted to provide a general overview, but I will also, well, my idea was also to provide some real examples, like do the final one for the canary release. So actually, this concludes my presentation together with the practical and the, let's say, philosophical approach. But we can discuss. So I'm open to new opportunities in this domain. So if we want to find something else, but we have Max here. Why don't we think about it?
Yeah, for sure.
Yeah, I think that there is some interest on going more vertical on some of the topics. Maybe some from the security side, some on the deployment side, the canary, and how the possible strategy, or how to test everything? Because you mentioned that test is important, but how to test everything in different scenario, in different deployment scenario, from local during the development, from the production.
And for a production testing phase, I believe that is the most important part to be sure that everything run well.
Well, I do believe that tests are key for a successful software lifecycle from end to end. Even if following the DevOps or GitOps stuff, there's no end to end. It's a loop, But I do believe that testing is fundamental at every level. So starting from unit tests. We live in a world where code is, if not 100%, at least 95% is completely deterministic. Because our code, when given some kind of boundary conditions, well, the result has to be a specific one. So we live in a world where the code is deterministic, like physics in before the quantum revolution. So it is our responsibility to test everything. So everything can be tested in very different ways, from the small bits, unit tests that are like particles. When I apply a force to this particle, it moves with a certain acceleration, but also to complex systems that are like fluids that respect different laws, because you don't see the particles, but you know that there is a pressure, you know that there is a temperature, so the overall state of the system can still be monitored and can still be studied and understood. So we need to test everything at every possible level with all the efforts. So this is something that we have to care about at every level.
I think that if you want to introduce some of non-deterministic behavior here, we can try to introduce AI and machine learning, deep learning stuff in a similar architecture.
Yeah, and quantum computing. Back to the origin. I'm a theoretical physicist.
Okay, so thank you so much for this presentation.
My pleasure.
I hope to see you very soon on this channel. And let me remember to everyone that if you have something to add or to ask, please leave a comment, and as soon as possible, we will try to answer. Thank you.
Thank you, guys.
Bye.
Thank you. Bye-bye.